All right. Yes. So I know a couple of people have already moved on for the holidays and have emailed me accordingly. This is Math Stat 341. What I'm going to do is the lecture of least squares. I've given this talk so many different times in so many different places. It's one of my favorite lectures to give. These are from a summer data science class that I've done with some colleagues across liberal arts colleges. And so this is going to build on what we did yesterday on the logarithms, and it's going to show some of the great applications of probability. What's also nice is you're going to see that some of the other classes you've taken, in particular multivariable calculus and linear algebra, are actually useful. You know, there is a reason why we actually have you take these classes before you take 341. Okay, so here is some data from a spring test. What is the first thing that comes to your mind when you see this? There's two acceptable answers. Yes. Positive correlation. What else? Linear. Okay, same as, yep. What else? There's another. Something else should be coming to your mind. Yeah, what are the units? So if you've never seen XKCD, XKCD is the favorite of many geek people. I think we should, give it one more. We should break up, and I can prove it. I think we should give it another shot. You see a nice plot of their relationship. Maybe you're right. I knew the data would convince you. No, I just think I can do better than someone who doesn't label her axes. Now, if you know XKCD, if you actually hover over the image, it gives you additional text. And the extra text is, and if you labeled your axes, I could tell you how much better. You could do a wonderful job, and we may do so later in the semester, of misrepresenting things based on what scale you display the data at. So you always want to add units when you're displaying things. It also helps give you a sense of what's going on. So let's do force in newtons, displacement in meters. I chose the data from basically y equals 5x. So if everything was perfect, I would get a slope of 5. Does that look reasonable when you look at the data? Yeah. You can see that if you go over 20 units, it looks like you're going up 100. So a slope of 5 seems quite reasonable. Having the intercept being exactly 0, that's a little bit harder. Looking at this, I'm sure I can see 0 is reasonable, but a small number could also be reasonable as well. The data is not good enough for something like that. And so, when we do the best fit line, using the method of least squares, we get 4.99x plus 0.48, which is pretty good in terms of the slope, but not as good in terms of the intercept. Which do you think is more valuable, the slope or the intercept? This is not like, which kid do you love the most? And when they were young, it was always whoever slept best the night before. The slope. Why is the slope more important?
Well, it does make sense that if you have 0 newtons, you go 0 meters.
Right.
But we're looking at how it's correlated in this case. The slope is going to be more helpful than that.
Right. So as x gets larger and larger and larger, the impact of the slope is going to be significantly more than the impact of the intercept. So I care much more about getting the slope right. Now, it turns out that there's other ways to do things. Instead of using the method of least squares, we could use the method of absolute values. And we'll talk a little bit about that. That gives a slope of 5.03 and a value of b that's less than 10 to the negative 10, which is basically saying, this is as close to 0 as you have any right to expect in an numerical simulation. All right. And so what I want to do now is talk about regression. So out of curiosity, how many of you have seen regression before? Okay, and of those of you who've seen it, how many of you have seen proofs of why it works? Okay. So the idea is to find best fit parameters. And so while it doesn't really matter, right now, the Ohio State has been moved up to number 2 in, what people, like Div 1 football for people who care about stuff like that. Yeah, absolutely go Bucks. But it doesn't really matter because, the big part of the season's coming up. The ratings don't really matter. V is talking about there is only one Ohio State University. This is very different here. We have 3 different ways at a minimum of measuring error. And so I believe y is equal to ax plus b. So given a value of xi, I predict I should have axi plus b. And so what I want to do is I want to compare what I observe yi with what I predict. And here are 3 different ways of comparing. I can just look at the difference. I can look at the absolute value of the difference, Or I could look at the square of the difference. One of these, is right out. Which, yes. Yeah, why is that bad?
Because that should be 0, and there's a lot of ways to make it 0.
Correct. If I give you 2 data points, bottom left and top right, what is the best line you would draw between them? Yeah, I like to be a pain in the ass. I would go from the upper left to the bottom right and have 2 large errors that are completely canceled. And so if you use the first one, positive and error and negative errors can cancel. Or if you want, you could have the error go to negative infinity. So clearly the first one is bad. What about the second versus the third? Absolute values versus squares.
Well, one sort of punishes bigger errors more.
Which one? The absolute value or the squares? Yeah, the squares punishes large errors more. If you have an error of 2, that is much worse than 2 errors of 1. So for instance, if you sneeze and you have 1 bad data point, that 1 bad data point will have a huge impact when you square. So that is a point in favor of the absolute value. There is a point in favor, yes, calculus. Why calculus?
It's relatively easy to take a derivative of a square. It's much harder to take a derivative of an absolute.
Yeah, and in fact, there's a reason why it's much harder. Yeah, it doesn't exist, right? The absolute value function is not differentiable. And so calculus is not available. At this point, this is like a poker game. The ante for this class is 3 calculus classes and a linear algebra class. So with 3 calculus classes under our belt, it would be nice to use that for something. And so the way I phrase it is, if I am being hired, I use squares. If I'm hiring someone, I have them use absolute values. If I use squares, I have all the tools and power of calculus at my disposal. All right, so what we want to do is we want to find the best fit parameters. And it's missing on the very bottom, which it says use sum of squares as calculus is available. This is almost like some coded text that you would have to scan just because it's like small little bits that are coming up. All right. And so there's a little mistake here. There should be a -1. There should be an inverse sign on the matrix. Let me just quickly review what's going on for multivariable calculus. So these symbols mean the partial derivative of E3 with respect to A and with respect to B. So in one variable calculus, how do you find the candidates for maxima and minima? Good, thank you. Check the endpoints. And I actually put some cheers there today deliberately to prevent myself from running into the board. Right? We have to remember to check the endpoints. And then we look for the critical points, places where the first derivative vanishes. Well, if I have a function of 2 variables, I can always fix 1 variable and then say if I'm going to be at a candidate, well, since I fixed 1 variable, then I now have a 1 variable calculus problem, and I need the partial of A with respect to the partial of B with respect to A to be 0. And the same thing holds if I fix A and then look at it as a function of B. So the only chance I have to be at a maximum or minimum is I need the 2 partial derivatives to be 0. I need the gradient to be 0, however you want to phrase it. I don't really have to worry about the endpoints because I'm looking for minimum error. I can send the error to negative infinity. I'm sorry, to positive infinity by just letting A and B get very, very large. So I know that I don't have to worry about the endpoints or the boundary. There's not going to be a Lagrange multiplier problem, that we need to worry about here. It's just find the partial derivatives, set them equal to 0. Now, when you look at these expressions for A and B, there should be a little bit of a fear or concern when you look at them. What are you afraid of? Oh, no. That is not acceptable. You cannot look at this and say this is not fun. This is simple sums. If you have even an Excel spreadsheet, you can do this very easily. This is not bad. And it's an explicit closed form expression. You give me the data, the X's and the Y's, which are known, and I have an explicit formula. I don't have to do any numerical searching. I don't have to do any approximations. I have an answer. Yeah, and then the bottom part of B, which is cut off, is essentially the same as the bottom part of A.
But it looks like somehow.
Yeah, so the problem is we could be dividing by 0. Fortunately, the only way you can divide by 0 is if you're an idiot. So imagine you believe that as you have an inclined plane, as you change the angle of incline, it changes how long it takes the ball to roll down. Okay? Is that a reasonable thing to think about for physics? That the time it takes for the ball to roll down is a function of how steep it is. What data would you like to collect? Angle and time. So imagine you collect data and every single data point has an angle of 30 degrees. And you now want to try to figure out how the time depends on the angle, given that all of your measurements are at 30 degrees. Are you going to be able to sniff out the time dependence? No. You will never be able to sniff out how the time depends on the angle if the angle is always the same. Well, if all the x's are the same, then xn times xn is the same as just pulling out the xn, which is the same as pulling out the x squared, and it's just 0. So clearly, if all the data is the same, it's 0. You know what this is? If I just divide by 1 over big N squared, this goes away and I get 1 over big N, the second moment of the x's, minus 1 over n, the first moment squared. The denominator is just the variance of the data x's. So as long as you don't have all of your x's at the same value, the denominator will be non-zero and the matrix will be invertible. So the only danger is if you try to understand how y varies with x and you don't vary x. And I love the method of least squares. It's a wonderful method, but it's asking a bit much to figure out how y varies with x if you don't vary x. There's the old joke of the person who is destitute. They're going to lose everything. They're going to lose the kids. They have no money. They have no food, and they're begging God week after week, just please let me win the lottery. And after 3 weeks of failure, they go, God, I'm about to be kicked out. Can you please help me? And you hear thunder and see flashes of lightning, and the voice of the Almighty is heard saying, can you meet me halfway? Can you buy the ticket? And it's the same thing over here. You should never expect too much from a method. If I don't vary x, the method should break down. So this is actually a really good sanity check. When you see something like this, and this is not emphasized nearly enough, this is actually an indication that we've probably done the algebra correctly. I should not be able to extract any useful information when the variance of the x's is 0. So this is a really good test. Right, so let's quickly go through the theorem. So this is a function of 2 variables. And one of the things that causes students some difficulty is that x and y are not the variables. X and y is the data. The variables are the a and b. And again, all of this is in a set of handouts that I will make available. I believe it is my most downloaded research article, although it's more of an expository article, just going through and doing these calculations. So the goal is we want to find the values of a and b that minimize this. So if we were to take the derivative of this with respect to a, the derivative of a sum is the sum of the derivatives. So what would the derivative of the item inside the sum be with respect to a? So 2 times the whole thing, almost, times negative xi. Remember, a is the variable. So when we take the derivatives, 2 whole thing to the 2 minus 1, and then the derivative of this with respect to a would be negative xi. I warned you, this is, I've been doing this for 20 years. It's just instinctive to make x the variable. X is not the variable. When we take the derivative with respect to b, it's the same thing, except we have a 1 rather than an xi. All right, so we said we want to have the gradient be 0. We don't have to worry about the boundary points. And so when we take the derivatives, as was just remarked, we get these 2 nice equations. And now what we want to do is we set them equal to 0. So clearly we can divide through by -2. And now we have 2 equations. And even though they involve sums, they're really 2 equations and 2 unknowns. The unknowns are just a and b. And so when we look at this, we get the sum of yn xn, the sum of a xn xn squared. Oh, okay, that's going to be pulling out an a, and there'll be a sum of xn squared. And so when we just go through and do the algebra, just rewriting it, the first one becomes the sum of xn squared times a plus the sum of xn times b is the sum of xn yn. And the second one becomes the sum of xn times a plus the sum of 1 times b equals the sum of yn. So this is just taking the equations we had here, just splitting the sums and the differences, keeping all the A's and B's on one side and moving everything else to the other side. All right, so I can write this in matrix form and just pull out the A and B, and now I have my matrix. And as long as this matrix is invertible, I can find A and B will be unique. So what's nice is there is a unique best fit line when we use the method of least squares. That's not the same thing as saying there's a unique best fit line. A very subtle difference. Depending on what method you use to find the best fit curve, you can get different answers as the best fit curve. If you are looking at a football game, what would you consider the best win? Huge blow, but which is a bigger blowout, 80-3 or 70-0? You scored more points in the 80-3 and you have a bigger margin of victory, but the other team scored. I would rather have the 70-0 than the 80-3.
And the goose egg is fun, it's true.
I mean, it's a nice problem to have. It's a nice problem to have. Yeah. Yes. 42-3 is fine. But I'm saying, depending on what you consider, you can come up with different decisions as to what is the best. And it's the same thing over here. But once I choose a method, it's nice if there's a unique answer with that method. There's one method using absolute values. There's one method using method of least squares. And each of these will give you a unique answer. And so here we have a closed form expression. This matrix will be invertible as long as its determinant is not 0. Yay, we're using linear algebra. And the determinant turns out to be the denominator we talked about earlier, and it is just the variance of the x's. So as long as the x's vary, we're fine. All right, is everybody comfortable with matrices? I've just put up a slide because it's been a while. If you don't like matrices, you can already, you can always do one of two things. You can talk to me or someone else, or you can just fake it and just go back. Well, I have a system of 2 equations and 2 unknowns. Let me solve for B in terms of A, and then substitute that into the first equation and solve it. So the matrices help you do the algebra in a nice unified manner, but we can always fake it. If I have a 2x2 matrix, we actually even have a nice explicit formula for its inverse. You do have formulas in general. This might remind you of Cramer's rule, which is sometimes done in high schools when they still did matrices. They removed that from the curriculum last year in Algebra 2, but they are bringing it back at least. Okay, so we have our formula. We talked about how we can rewrite the determinant, and this comes down to one of the themes of the semester, finding a good way to look at the algebra. And the idea was to notice that if I look at this, product of sums and the difference, if I multiply by 1 over n squared, it's now essentially looking like the variance. And so again, so much of mathematics is, can you find a good way to look at the quantity and interpret what you have? And interpreting this as the variance is extremely valuable. Okay, so this is just going through and just doing the calculation and coming up with alternate ways of writing the formulas for A and B. It really doesn't matter. I'm glad I have this now, because earlier there was a comment that the formulas didn't look nice. There's more than one way to write them, and so hopefully one of these formulas looks nice for you. Doesn't really matter. I particularly like to use this version because if you have an Excel spreadsheet or a Google spreadsheet or something like that, it's very easy to just have columns and just work with that. Also, of course, if you're doing something with R, you're just summing elements of vectors, feeding it in, no problem to do something like this. Okay. And then, one of the things you always want to do is check and see, are the units right? Do the units match? I will, leave this slide in the notes. So if anybody is interested, you can just go through and look at this, but it's always worth doing a unit check. What should the units of A be? What should the units of B be? Well, for this, I'm saying if X is in meters and Y is in seconds, then B has to be in seconds, A has to be in seconds per meter. And then you can go through here and check and see, does this have the right units? And again, it's not a proof that you haven't made a mistake, but it's a good test if all the units match. Okay, I'm not going to go through solving equations. I'm assuming everybody's comfortable doing that, but if not, just talk to me. All right. Somebody give me a famous physics law. Yeah. I want a physics equation. E equals mc squared. And so there you have energy is proportional to the square of the speed of light. So that's unfortunately not a linear relationship. All right, somebody give me another famous physics law. If you did Einstein, who should you do? Newton. Oh, yeah, F equals ma, but I prefer his gravity. Force is equal to the g times the product of the masses divided by the square of the distance. Again, non-linear. So unfortunately, the method of least squares works beautifully to find the best fit straight line, but most relations in the world are not straight lines. So we've either developed a method that is wonderful, but very, very localized, or it might actually have great applicability if we can convert many things to being linear. Fortunately, we just had a lecture earlier, in the semester, i.e. Friday, on converting things, right? And this is one of the reasons why we care about the logarithm. And again, how many of you have ever seen this emphasized before as to why we care about the logarithm? So at the very least, some value has been added this semester, that there is a reason we look at this function. And this is in some sense, one of the biggest themes of linear algebra. Linear algebra is all about finding the right way to look at things. If I give you the equation of an ellipse, it's not that hard to graph it. If I give you an ellipse and ask you for the equation, can you figure out what the equation is? And so let me see if I can toggle back for a second. So if I give you something like this, here's minus a, here's b, minus b and b. Can somebody give me the equation of the ellipse?
X minus a squared plus y minus b squared.
Nope. That would be the equation of a circle centered at AB. Nope. It's got to involve x's and y's. So x over a squared plus y over b squared equals 1. Notice in this special case, when a equals b equals r, it reduces to a circle. So again, this is a nice smell test. Is this reasonable? Yes, if a equals b equals r, it's a circle. And if you think about this, when x equals a or negative a, then y equals 0. Oh, good. Okay, when x is equal to plus or minus a, then x over a squared equals 1 and the y equals 0. Similarly for the other. So this is the equation of an ellipse centered at the origin, aligned with the coordinate axes. Now, I could decide to have some fun. And what I could do is I could give you the ellipse, but now it is not centered at the origin. Does anybody remember how to do the equation of the ellipse if it's not centered? I'm sorry? No, you say, I think you're on the right track. You use a rotation. So let's look at this new coordinate system UV. Basically the UV coordinate system is you just lean back, right? I was worried about doing that after walking in the wet grass earlier today, but good, traction held. So if you lean back in the UV space, it's just a standard ellipse aligned with the coordinate axes. So what you do is you take a rotation matrix and you rotate to UV space, solve it there, and then rotate back. So I'm not going to go through all the details, but this is essentially the power of linear algebra. Linear algebra is all about finding the right coordinate system to attack a problem. That's a huge, huge part of the course. And you might have heard about something called like the principal axis theorem, that if I give you a real symmetric matrix, it has a orthonormal basis of eigenvectors. These give you the right directions to decompose the transformation. And it's essentially telling you something along these lines. So let me go back to sharing the screen. It takes 3 seconds to load. Okay, so what we want to do is we want to find, for nonlinear relationships, a way to look at them so that they are linear. We basically want to change variables. And it's just going to be a little bit more involved change than just rotating our axis. But morally, that's what you should be thinking about. It's something you've seen before. This is why the logarithm is so important. This is how it fits in the big picture. All right, so we did y equals ax plus b. All that really mattered was that it was linear in the a and the b. I could have had, ax squared plus bx plus c, or ax to the fourth plus bx cubed. It doesn't really matter. It would just change the size of the matrix. So more generally, I could assume y is a linear combination of some functions f1 through fk. And these functions could actually depend on multiple inputs as well. All that matters is that the unknown weights, the coefficients a1 through ak, are only occurring linearly. And then I would just have a k by k matrix, and the analysis would be very similar. All right, so if we take Newton's law of gravity, g m1 m2 over r squared, let's say we guess that the force is proportional to the radius, which makes sense. The force depends on the distance from the radius, but it could be an exponential decay. So it is a bit of a guess to say it should be r squared. There was a beautiful argument in Feynman's classic series of lectures on physics, where he describes why gravity should be a 1 over r squared force. And he said, imagine you have a point source and it's providing some yankage. It's pulling things in. The total amount of yankage is the same no matter how far out you go. And so what is the surface area of a sphere of radius r? 4 pi r squared. So the surface area is proportional to the distance squared. So if the yankage is supposed to be constant, then the amount that you feel at a distance of r should be like 1 over r squared, so that the product is constant. So this is a nice argument, and it says that if you lived in a two-dimensional world, you would have gravity would be a 1 over r force, and there would be infinite amount of work to do certain types of motion. And so the world would be a little bit different. But anyways, let's say we believe force is proportional to radius.
Let alone the fact you'd be in a two-dimensional world.
Yes, and then we can talk about eating, and then the after effect of eating as to what you do with there will be some real issues if you are a two-dimensional being. So if we take logarithms, we get the log of f is equal to a log r plus b, where little b is the log of big B. And now notice we have a linear relationship between the log of f and the log of r. So a power relationship becomes a linear relationship under logarithms. So I grabbed 25 of the most populous cities a couple of years ago, and here are their populations. And again, it always depends on what are you defining the city to be? Are you doing the city, the metropolitan region, the municipal government? Doesn't really matter. Here is a plot of the rank and the population. So obviously, the most populous city are going to be the lower rank. If I do a plot of the rank versus the log of the population, this is called a semi-log plot. Doesn't really help me. But if I do a log-log plot, plotting the log of the rank versus the log of the population, that looks like a pretty good straight line. Not perfect, but not bad. Another one, 100 of the most populous cities. And you're again doing a log-log plot. Again, you see a really nice straight line. There's lots of different examples we can do. Here's word counts, the plot of the rank of certain words in English and their frequency. And again, when we do a log-log plot, it's not perfect, but again, going over several orders of magnitude, you see that a really nice overall linear relationship. And frequently what we're trying to do is find the main term to describe some behavior. All right, so what I want to do is I want to end with a couple of examples, and then we will do an extra credit game. So it'll be the people in class versus the people who are not in class. My money is on the people in class today. And so this is a real world challenge. So I serve on a regional school committee. The 3 schools, Williamstown and Lanesboro Elementary and Mount Greylock, the regional middle high school, have a budget of say on the order of $21 million. We get around $3.5 million in Chapter 70 funds from the state. Before we regionalized, we were 3 school districts. How many committees do you think we needed for 3 school districts? Yeah, very good. We were actually 4. So there was, or depending on how you count, 5. So each building had its own school committee. Then there was a joint committee of the 2 elementary schools, which was composed of members of the school committees of the 2 elementary schools. And then there was a joint committee between that committee and a subset of the, so I mean, it was an administrative nightmare. And you would have the senior administrators having to do sometimes 3 copies of the same meeting. Let's review policy, but now I have to do the policy review for each elementary school. So it was ridiculous. There were lots of reasons to regionalize. This was one of them. But if we regionalize, the state would no longer tell us how much money goes to each building. They would only tell us how much money goes to the district. And it was very important that we keep track of how much money each building was getting, because we needed to assign how much each town had to pay. So each town had to get the right credit. It would have been very easy if we were given the formula, but we weren't. But we had a lot of data. And so I said, hey, look, I am quite happy to try to sniff out the formula. And so I wanted a formula that was fair, that did a good job predicting, that was transparent, and that could be explained very easily to finance committees, select boards, and voters. And so I decided to use the method of least squares. And I used only really 2 pieces of information: the population of the students in each building and the property value assessments of the 2 towns. And so there's a couple of things you want. You want the solution to exist. It's going to give you how much of the money goes to each building. So those numbers should be between 0 and 1. They should sum to 1. You should divide up all the money. You want it to be stable under small changes. If a few students leave or a new building is constructed, it shouldn't wildly change the allocations. That's a disaster for town managers if you have that much variability. And it turns out that for the most part, this can all be done. If all of a sudden 40% of the kids die and 50% of the buildings burn down, we have moved so far from the baseline that you can no longer trust the results there. However, if 40% of the kids are dead and 50% of the buildings are burnt down, I think we have bigger problems than how we, assigning, we're basically trying to find like the zombie apocalypse or something at this point. So in the region that we're looking at, it's actually pretty stable. And so here's, the data for a couple of years as to what percent went to each building. And so using this, I actually predicted, I think it was 2018, before we actually got those numbers. And then when I compared my predictions to what came out, this was before we regionalized, we were off by around $10,000 at most per building. Out of 3.5 million, 10,000 is essentially within noise, in terms of just predicting versus what it actually is. And so this allowed us to say that we actually could assign the money in a reasonable way. So I will talk a little bit more about this at the end of class today. For the next one, we've talked about if we have a power law, if we take logarithms, it becomes linear. One of the ones I want you to do for homework is Kepler's 3rd law. So Kepler has 3 laws for planetary motion. The first is planets travel in ellipses with the sun at one of the foci. So not so bad that we spent some time reviewing ellipses earlier today. The second is if you draw a line from the sun to your planet, then it sweeps out equal area and equal time. And then the third is that the square of the length of the semi-major axis of the orbit is proportional, the cube of the length of the semi-major axis is proportional to the square of the orbit. So t squared equals b tilde L cubed. As soon as you see me calling the constant b tilde, what should you be immediately thinking? What's b? B's got to be the fundamental object. Well, I might as well just take the square root of both sides, and rather than saying t squared is proportional to L cubed, I would then get t is proportional to L to the 1.5 or 3/2. When you're talking about it, it's nice to have integers. People like integers, and they'll say period squared, semi-major length cubed. So imagine we didn't know this. Could we discover this through statistics? And so here is the data for the semi-major axes of the planets. I'm using astronomical units. That's basically the distance from the sun to the earth. And I'm doing my orbital measurements for how long it takes in units of years. Is there any planet that we should look at that would help us figure out what B is? Earth, right? In the units we're looking at, we've chosen things so that Earth has a distance of 1 and an orbital period of essentially 1. So in these units, B is essentially going to be 1. So it just makes things nice. So there's a bunch of fun units in the world. There's the Bruno, the Millie Helen, the Slug, the Smoot. We've talked about the Smoot before. If you haven't heard the other ones are fun as well. And so for your homework, you are going to try to do this. I can't remember if I give you, let me see. No, I have adjusted it. I am old enough that I think when I started doing this, there were more planets than there are now. It's not that a catastrophe has happened to one of the planets. It's that we have downgraded Pluto, and Pluto is no longer considered a planet. And so when you look at this, you have an incredible fit. When you look at this, this is a log-log plot, several orders of magnitude, beautiful fit of everything on the line. And to me, this is one of the most powerful pieces of evidence in favor of the method of least squares, that you are able to predict things like this so beautifully. Just because I want the lecture to be complete, we've talked about this bridge before in the Boston area, so I know you've heard the story before. So if you are a fraternity in the good old days, you could do a lot of things. And that's one of the reasons why we no longer have fraternities operating as they did under the good old days. It is actually a fascinating story as to how fraternities came to Williams campus. I am happy to talk about that when things are not being recorded and what happened to get fraternities away from the campus. But they decided they wanted to see how many times it would take them to pick up and drop one of the pledges along the length of the bridge. And they saw it was 364.1 Smoots, that was his name, plus or minus an ear. The Cambridge police didn't like this, and so they erased all the Smoot marks. The fraternity didn't like this, so they did this again. It's now been institutionalized, as you remember. And now when accidents happen on the bridge, they tell you at what Smoot mark did the accident happen. And then the reason I love telling the story, never hurts to hear this one again, is you never know where opportunities will lead. And so Smoot became the chairman of the American National Standards Institute and the president of the International Organization for Standardization. And I just love imagining him when he's asked you, what are your qualifications? Well, I don't mean to brag, but I am a unit of measurement myself. There's lots of other problems you could apply this to. We talked about the birthday problem earlier in the year. And what if you have not just 365 days in a year, but what if you have D days in a year? And we did the analysis that it's proportional to the square root of D. It's D to the 1/2 times the log of 4. If you look at the data and try to do a best fit line, there's a bit of a spread, but you do get the slope is about 0.5. And I did 2 different sets of 10,000. And so again, when we're talking about the most important thing is the slope, we're able to express that without too much trouble. All right, so what we're going to do is we are going to have a contest for the rest of the day for those who are here versus those who are not here. And so let me just stop the recording.